Welcome back, my structural analysis friends. In today's lesson, I'm going to show you some shortcuts for computing deflections of beams. We've been studying the methods of conjugate beam and moment area for some simple hand calculations, but in practice, those are kind of lengthy and time consuming. So I'm going to show you some tricks that professional engineers use by utilizing design charts and design tables to help come up with these similar equations that are already tabulated for you. So without further ado, let's get started. The method I'm going to show you for using these design charts for computing deflections is known as the method of superposition. Okay. Now, a lot of these calculations that we've been looking at are very classic and they've been derived, and there's no need to repeat these calculations other than as a theoretical exercise or an understanding of the mechanics. But in practice, we don't go back and redefine these equations every single time. They never change. So what engineers have done in resources such as textbooks or design codes is they've tabulated certain cases and provide equations for those. And so I'm going to show you a couple of them. The first one I'm going to show you is our textbook, which is the Casamali 5th edition. And so if I pull that up here, inside the front cover of this, we can see there's a chart that looks something kind of like this. And this is generally the basic format of what we have. Now let me zoom this out a little bit so we can see more of them. But you can see that for a simple case such as, and they've got 8 or 9 different cases inside the front book, and other resources have a lot more, but the Casamali sticks to some basics, is that if we have a point load on a cantilever beam that is a distance of A from the chart, or from the wall on this, then we know that we can find the shear moment diagram. We could go through do our moment area calculation every single time to come up with the displacement. But instead what they can do is they can come in and say, well, these equations that we derive using those methods, whether it's double integration or what have you, that these equations will never change based off of the parameters of the figures. All right. So in this particular case, because of the point load being here, that there would be 2 different regions. There's a region to the left of the load in which the beam is flexing, and then there's a region beyond the load in which the beam is just extending down further. And in fact, that extension that's happening here is because of the slope change at the location of the load. Okay, and then there's no flexing beyond that. There's no moment in this piece that's outside of this. But here are the equations for the slope and the displacement for each of those cases. So 0 less than x less than a, these are the slope and the deflection. So that's what's going on when x is measured from here to here. And then likewise for a less than or equal to x less than or equal to L, that's the portion beyond. This would be the set of equations as well. And so it's kind of interesting, and they have lots of different cases. Here's the concentrated load, here's a moment. Here, if you go down a little bit further, we've got distributed loads and so forth and so on. And you get into some even more complex ones over on the other side. Maybe you need something with a moment on the end of a simply supported beam, okay, or a point load that is off center. Now, something that's interesting in some of these cases, in particular with regards to like the point load, what you can see is that again, we've got our regions, 0 less than x less than a, and here are my equations, and then a less than x less than L, it would be the region over here, because the curve is not the same on either side of this. Okay, and then likewise the slopes at a and b are different for calculating this. But then when a is greater than b, and then they actually give you some shortcut equations for things like the maximum displacement, and it would be this equation, and then its location of maximum is not necessarily underneath the point load, it's off center because of the curvature of the beam having to happen here. That in some cases they even give you the YMax function. Now I'm going to warn you, and we'll talk about this in a little bit, that YMax, it's a little dangerous to use that unless you're absolutely sure that if you only have one beam, or one load case, such as a point load on this beam, and these equations work, it works without a problem. But the moment you start doing superposition, which we'll talk about here in a second, these guys start to have some problems if you're not careful. And I'm going to try to point some of those pitfalls out for you. And if you go down a little bit further, we've got more useful equations. This guy also has a YMax, so it will apply to that. So in this particular book, our Casamali book, you can see that, we've got a few simple cases. Here's the uniformly distributed. This one's almost worth memorizing because we use it so much, and then we've got, a moment in the middle, all sorts of different cases that happen. Now, one other thing to notice on this is you got to pay attention to where they're measuring X from. And all of the examples in this book, it appears that and usually it's indicated on the picture somewhere, you see this little arrow with an X right there. It tells you that they're measuring X equals 0 as the left end. And that's been the convention we've done in this class. But there are design aids out there where they will move that and go from a different way to make the math a little bit easier, or the algebra easier, or it's just a different standard way of doing things. So you've got to watch that guy, and I'll show you how to handle it when your X is somewhere else other than what's happening here. So but for now, that's our Casamali text. So there's several cases for that one. Another useful one is the American Institute of Steel Construction Manual, and this is the 15th edition of this book. If you flip to the back of chapter 3 in this, there are tables upon tables upon tables of shortcut cases for similar things. This book is a book that you'll need when you get to your steel design class, and for my students that will be next semester. And you will be buying this book because as a structural engineer, this book is invaluable just for the pages I'm getting ready to show you. Okay, we have a ton of cases for this. In fact, this one goes so far as to say not only do they give you deflections, the deflection equations, they also give you shear and moments and what the basic shear and moment diagrams look like for all of these. And so superposition, we can start to kind of add all of these things up. One thing to recognize is that the AISC manual does not give you the slope directly. Okay, but what they do give you is they give you a function for the displacement as a function of x. Okay, and if you remember, if this is my y equation, the slope is the first derivative of this. So I can take this equation, take the first derivative of it, and I now have the slope equation. And I have that for a wide array of cases. In fact, there are a lot more cases than what were in the Casamali text, just because these are capturing what practicing engineers see. I mean, I've got, things, whoops, hit the camera there. I've got things like triangular loads. I have things like, point loads off center, which you've seen before. I have 2-point loads that are symmetric. And if you keep flipping back through here, if we get all the way back to the end of this thing, you can see that there are, looks like 36 different cases defined in this book, and all of them are different. So this one has a lot more equations to use. They even go so far in these design aids to give you shear and moment diagrams for things like continuous beams. Okay, which this is pretty handy because this is a statically indeterminate structure, but engineers face this enough that based off of my load patterns, for a case where I load 2 bays and 1 off, here are my diagrams for the shear and moment, and then it's just a function of the load and the spans to come up with these coefficients. It's super, super easy, and I don't have to do all the structural analysis stuff that we've been learning in these last couple of lessons. Okay, so learning how to use this manual is a very, very useful thing. And as a practicing engineer, you should have this on your shelf because you never know when you'll need it. These, 8 or 10 pages of shortcuts right here, in my opinion, pay for the book. Okay, just because all the information that's here, and it's I will jump to this before I will pull out moment area or I pull out conjugate beam. I will jump to this book first. It's only in cases where I don't have a load case covered by the techniques I'm going to show you that I will do something else. But anyway, I wanted to kind of show those to you, and those are kind of my cases. Now, both of these, the Casamali and the AISC manual, have some limitations, okay, and some major assumptions that are taking place in this. Okay, the first thing, and this is one that we've kind of talked about throughout the series, is this this assumption of LEIH, right, which is what we call our mantra for structural engineering, and that is that this is an acronym for 4 properties that have to be maintained. We use this to allow for small displacement theory, okay, in which the sine of theta is approximately equal to theta. If I follow these 4, I can say that, and if that applies, then I can apply the principle of superposition as well. So it's the same assumptions, and if you remember, the L is linear behavior, which implies that if P is my load and delta is my deflection and K is my stiffness, that there is a linear relationship that exists between these. That is, if I double the load, and say I put 100 pounds on a beam and I get a deflection of 1 inch. If I put 200 pounds on the beam, I will get 2 inches. It's a linear relationship. If I triple it, it triples. Okay, now certain structures like cable structures are not linear structures and they violate this L guy, so these methods will not work for him. But for beams, most often this will work. Okay. The other assumption is that the loads are small enough that the beam never leaves the elastic region. Okay, that I don't get into some sort of permanent deformation or plastic behavior in the beam on those. This is what we call the elastic region, and if you remember, the elastic region is what gave us Hooke's law. That signal is equal to E epsilon, and basically if I put a load on a beam in the elastic region and then I unload it, it will rebound back to its original position. There's no permanent deformation. Okay. The other two are important, but probably not as important, especially for most engineering materials. These are isotropic and homogeneous. Okay, these are material property requirements. They have to do with the orientation of crystals in a given direction or versus the orientation of the crystals throughout the cross section. And so those will pretty much assume, especially for steel, that we're okay. Generally, for most structures, it's a fairly reasonable assumption that this applies. Especially for metals. Steel, no problem. You start getting into certain types of concrete and certain types of plastics, that might become an issue. So you got to be kind of careful when using it. But if you maintain that all my displacements are really, really small, it will work nonetheless. So it's kind of a major assumption. But we have to follow these four. Okay, so make sure you know those four assumptions, because if I violate any one of them, then all bets are off on the method that I'm getting ready to show you. All right, so let's show you what the method of superposition is. Okay, so I made up this kind of a trivial little example here in which I have a simply supported beam that has three different loads on it. It's got a distributed load on it, it has a point load, a distance of A from the left end, and then it has a concentrated moment at the end. All superposition says is that if LEIH applies, I can turn that one picture into three simpler cases. Okay, so I could turn it into a simply supported beam with an M naught on it, and I could analyze it for deflections and displacements and what have you. Okay, and then I have a uniformly loaded beam that I could analyze it for that, and then I have a concentrated load at a distance A from the left end, and all three of these are in your book. Okay, and all three of these are in the AISC steel manual. And then all I do is I take the equations as a function of X, and I can add them together. Okay, and so this would be a Y1 and a Y2 and a Y3, so forth. And so if I look these up in the book, and like I say, we flipped through these, but I went ahead and pulled them for you, that for beam number 1, which was the concentrated moment, Y is a function of X. And again, X on all of these, according to the book, X was measured from the left end. So when you go and you start setting these up, you have to make sure that your references are at the same point. And in this case, they are. Okay, that everything was being measured from the left for all three of these diagrams. So I can just simply add these as functions of X. Otherwise, you would have to do a shift that I'll show you here in a second. Okay. All right. So for the moment case, that was this guy up here where the moment's on the end. This is my equation. And you see it's a minus m over 6EIL and then x cubed minus 3LX squared plus 2L squared x. And that equation is valid on the interval of x being between 0 and L. Anywhere along the beam, this is the equation. Okay. And I did these out of order. Let me jump down and do number 2 next. That y of x is this function. This is the distributed load over the full length. And again, this is the equation for 0 less than x less than L. Okay, the one that's different is the second one. Okay, or sorry, the third one. My second one on my list, but number 3 on the picture, this guy. Okay, that the equation for the curve is different than the equation for the curve here. Okay, and so we have to figure out where's the point that I'm interested in. If I'm wanting a point, the deflection at a point to the left, I'm going to use the case where 0 is less than x less than a, and I use this equation. Okay, and then if I want a point for b, then I use this one. Okay, so depending on where you're at, but you have to account for all of the L. And when we get to virtual work, this will start to make a lot more sense and be a critical element of what we do as we start to try to figure out energy calculations off of these displacement criteria. Okay, so then if I want the total of this, on the interval of 0 less than x less than a, I add case 1, and this one of case 3, and the one down here of case 2. And then likewise, if I want the other side of it, I add case 1 plus the second case of case 3 and then case 2. And that gets me a combined function for y as a function of x. Now, the thing that's cool about that is that this is now a function, okay, and I can use all of my calculus principles to find minimums and maximums of those kind of things for using first derivative and solving for x and all those things that you learned back in calculus. All that will apply, and you can use that to find YMax. Okay, in fact, that's probably the preferred way of doing things. Okay, now, there are some pitfalls and things that you have to look out for, and that's what I'm going to show you next. Okay, The first one that I'll warn you about is inconsistencies between design aids. I mentioned this one earlier, that X has to be measured from the same point, and there are issues with the way people that create these design aids label things. Okay, so you got to make sure that you're measuring from the same point, you're measuring in the same direction, okay, that and that your origins are at the same point. If they're not, you have to do a shift that I'll show you down here on the next step. Okay. One problem that's real common, and this shows up especially with regards to cantilevers, is that if I have a cantilever at the left end and fixed on the right, I don't have this case in the book. Okay, but what we can do is we can take the case from the design aid where X was measured from the wall or the fixed end to the right. Okay, and so on this picture, that would be like saying my X is measuring from here. Okay, and then I can redefine that if I need the left end, I can redefine my X, my coordinate as an X prime or something from the left end as a function of this X value. So if this beam is L long and I need a reference from the left end that I'm calling X prime, but my equations are measured from the right end as a function of X, then all you have to do is just do a simple remap that says, well, for any point on the beam, say here, I am X prime from the left end, and I am L minus X prime from the right end. Okay, so that means that X prime is L minus X, right? It's the exact same point on the beam depending on which coordinate system you're in. And then what I can do is I can then, if X prime is L minus X, then I can take and solve for X, the variable X, as being L minus X prime, and then anywhere in the design aid that I pulled the equation from here, I substitute this in for X. Okay, so it might be 10 feet minus X prime, as being the point that I'm interested in, and then that will be what goes into the equation. So you can always shift it using this idea that we can substitute into our design aid equations for X. Okay. The other one that we've mentioned is that equations for YMax, the maximum displacements, do not work unless they occur at the same location for all of the parts. All right, and so I'll show you an example of this. Fairly simple. The first one is the one on the left. So if I look at that, so I've got uniformly loaded beam with a point load exactly in the middle. Well, when I do my superposition, I do the uniform case, and YMax is located at L over 2. And then I can look at the point load case P, and its YMax also at L over 2. These two, I could take the YMax equations for both of these cases, and I could add them together, no problem. Okay, and they occur at the same location. But let's consider something a little different. How about a distributed load on a beam with a cantilever, right? And so we can kind of look at our deflected shapes. For my first case, I do the distributed load over, and that should continue on a little bit. I just realized that. Get that onto the picture. Okay, that it's a W load over the entire thing, that I get a beam that wants to deflect in the main span, and depending on the dimensions of this, it might curl up or it might curl down a little bit. But my YMax, say, in the main span of this thing would be this value and located, and we don't know where that is. It depends on the parameters on where that point is located. Okay, for the case with the point load, now my YMax is out here at the cantilever tip. Okay, now they might give you a YMax back in the backspan as one of the equations. In fact, I think the AICS Manual does give you one, and they also give you the location of that X, but you have to make sure that if I'm using this one, that YMax is at the same location as the one that's here. It may not be. And if it's not, then you have no other choice but to not use those particular equations. You got to be very careful that all these points line up when I'm looking at the point that I'm after. Okay, so in this case, obviously YMax 1 is at a different location than YMax 2. I can't add those and say that these two guys together are my YMax for the beam. All right. In fact, in this case, they're fighting each other. Right? This load is pushing the beam up, whereas this load was pushing the beam down, and so they're actually subtracting from each other and tending to zero out. Okay. Okay, so we can't add the values, but what we can do and what we have to do is what I explained earlier, is I have to compute the deflection as a function of X for each of the separate cases, Y1 of X and Y2 of X, and do the algebra on this to write the equation for Y of X. Okay, and then once I do that, then I can use my calculus to find the YMax. Okay, so that's a very, very important step to be able to do. So it's not too hard. The design aids are very, very useful, and they make life a whole lot easier when you're trying to do some sort of quick hand calculation, especially in the case of the steel manual. So I hope this has made some sense to you. Design aids, like I say, you'll use those probably more than you'll use moment area and conjugate beam in practice. So I thought it would be worthwhile to at least give you kind of a quick talk on how it works and what the assumptions are. But make sure you remember the assumptions, LAIH, you have to follow that. That assumption throughout the structure sequence that we're doing here is very, very important, because it allows us to not only do superposition, but it also ensures that we have what we call small displacement theory, okay, and which allows us then to, add and make some assumptions with regards to stresses and strain behaviors and deflections and things like that. So anyway, I hope it's made sense. It's a quick one. Let me know if you've got any questions. Toss us some comments down below, and we will get back to you. And otherwise, if you've liked the video, if it's helped you out at all, please toss us a like, and be sure to subscribe to the channel for more videos that are coming. And we will see you guys next time. Happy engineering.